Hi, science class. Today we're going to start chapter 2 in our physics unit. And this is exciting because this is our last chapter and our last unit and our last set of notes. So we're getting closer and closer. One fair warning for this one, please make sure we're doing lots and lots of practice and make sure you have scrap paper handy to draw out the pictures of how these physical or these reactions or these collisions are going to actually happen. We're going to have lots of examples of different types, so make sure to actually draw out an image. And I did my best in these notes to kind of help you along to think through the process so you understand what's happening and what should you expect. So I started to introduce these a little bit in chapter 1 when I talked about force is equal to mass times acceleration and we talked about Newton's laws. So we're going to dive into them a little bit more in depth and really understand what each law actually means. So here is Newton's first law. And we see this is the law of inertia, or talking about how an object in motion stays in motion. And this might not make sense right away because you think to yourself, well, once I set something in motion, it doesn't. It just falls to the ground or it'll stop. Nothing can keep going forever. Well, that's right, because there is these unbalanced forces or these forces that, well, Newton was first to discover that we always kind of knew were there, but no one actually explained them, like gravity. And we know gravity. Oh, yeah, right. Gravity always pulls things down. Or there's friction. We never have an entirely frictionless surface. But if we could create a perfect scenario where we're in outer space, where there is zero friction, zero other things to hold something back, if you were to throw something in outer space, it would just keep going forever and ever, and it wouldn't accelerate, it wouldn't speed up, it wouldn't slow down. It would go until something acted upon it to stop it. And so this is his first law. An object at rest will stay at rest. An object in motion tends to stay in motion. Both have that same inertia, keeping all that same velocity. That was his first law. So talking about these reactions and talking about it, we're jumping to Newton's third law. And this is where every action has an opposite and equal reaction. And so the force on one that acts on 2 is the same as force number 2 acts on number 1, just in the opposite direction. And you can imagine from this picture below, two people on skateboards, so trying to reduce friction as much as possible. If they have one person pushing off, well, both are going to be set into motion, or both kind of push away from it. There's going to be a force on the person pushing as well as the person being pushed. And so that's Newton's third law, tying in with this inertia law that we just learned about on the last slide. And so if you were trying to think of this as jumping right on a skateboard, so the skateboard's staying still on a gravel road or on an asphalt road, and then you try to jump on it and leap off, well, the skateboard's going to go flinging back and you're going to go flinging sideways, and there's this opposite force and you're not on firm ground, right? So there's going to be that backward slide of that skateboard. And so that's the opposite and equal reactions. And this law we talked about from chapter 1, so I left it second. So we have Newton's second law, and this is where force, mass, and acceleration are all tied together. So mass times acceleration equals this net force. We're going to keep it very, very simple in our lesson here, and we're just going to be talking about two things, and we're going to be talking about perfect situations, and for the most part, we're removing gravity, we're removing all this frictional forces in our imaginary situations, just practice with as few variables as possible. So we're going to practice with these theory questions right to start off with. Here we can see we have a simple problem and we put these two people on ice to essentially say, okay, friction is negligible. We're not going to think about friction and we're going to have two people push off from each other. So essentially we have FA equals the negative FB. we put in what force actually equals because we don't have a force to say they're equal. So we're going to talk about their mass and their acceleration, things that are measurable. We have to solve for acceleration. And so we divide by our mb off of one side, and what we do to one side, we do to the other, isolating our negative acceleration on b. Now we can actually put in our numbers, and we see we have the mass of A is 80 kilograms times by the acceleration of A, 3, so 80 times 3. Then we divide by 60, which will equal 4 meters per second equals negative A. But how does that work? We don't just have this negative over here. So we want to move the negative over here, and we want to add a negative here, add a negative over here, and we want to move it over to our actual answer, thus canceling them. And so this just makes sense in our head where, oh, right, we're going negative 4 meters in the direction, because it's not just that it's the minus 4 meters. It's not just this number line where we're thinking it's less. We're using them as directions because we are in vectors, right? So we want to talk about these directions. And when we push off of each other, we're going to move in these two opposite directions. So now our number makes sense for one moving in 3 meters per second. The heavier one will move slower. The lighter one will move faster, just in an opposite direction. So let's practice the second one and let's go a little bit quicker. We can see now we're dealing with much larger masses, much larger speeds and accelerations. So we have these two different things. We're going to use the exact same formula because we're talking about these Newtonian laws where two forces are equal when we're coming in to collide. Here, mass times acceleration, mass times acceleration. Here, we again isolate for this acceleration, keeping our negatives in order. And so this is why it's so important. The negative is telling us the direction. So we need to keep this negative in our formula. And we're going to see why once we solve it out. So once we substitute our numbers in, we see we have negative here, and these are going to cancel. Now all of a sudden, we're moving in that positive direction. So here we see another question, except now we're trying to isolate for our mass. So same, except we're starting here and we need to isolate our mass. We do the exact same thing, but one notice we should pay attention to is this negative I'm attaching and I'm keeping with this acceleration because it is the vector. It has the direction. Mass is scalar. It cannot have a direction tied to it. You can't have a negative mass because you just have zero mass. You can't have negative mass. So we have to remember that the vectors are tied with the direction. So when we have it, now, as we can see, we have 750 grams. We have two accelerations, one in the positive direction, one in the negative direction, and this is where it's going to get confusing because we have to make sure we're keeping with the directions. And I highlighted it in brackets where I had my acceleration for B is still a positive, however, it was tied with a negative acceleration. So it's still positive 15, but there was a negative acceleration tied to it right here. And so that's where it helps to keep and make sure that you track where these negatives are becoming. Because as you can see, this 750 grams times by this negative 13 meters per second divided by negative and then the positive, so it'll essentially be negative 15. My negatives will actually cancel out. And so this negative will cancel out with this negative, giving me once again an actual positive mass. Well, it's scalar, right? You can't have a negative mass. So that was very important why we need to track our negatives. The one thing I also wanted to note is because I had nothing else extra, you can convert 750 grams into kilograms. However, I knew my meters per second squared were canceling here, my meters per second were canceling here. And so always good practice, try to go into kilograms, but I knew my grams were going to be left and I didn't convert, but good practice if you wanted to. You could also convert. You would get the exact same answer as well. Okay, now we're going to actually get into the meat and potatoes part of our chapters, or our whole kind of last chapter. Momentum. And so we're going to actually think about what this is. So here's a question. What would you rather have fall on you? Hopefully we thought the tiny raindrop. Why? Well, mass has a huge part when tied to velocity. And so when we talk about mass, we know it's going to hurt a whole lot more traveling at 100 kilometers an hour rather than a tiny little raindrop. And so this is where it's going to play into our momentum formula. So we can see here, this P, this new symbol that we're going to have, is what we're going to use as our symbol for momentum. And so this P, or momentum, is equal to mass times velocity. So a very straightforward question to start with is 21 kilogram object is moving at a speed or velocity of 22 meters per second down. The only trick to this is we have a negative direction. So it's 21 times by negative 22, getting us a negative 462 kilometers per meter per second. So let's pick it up a little bit. Here now we have a motorcycle and its rider moving at this amount. So this kilogram meter per second, that's the units for momentum, moving in the south direction. Okay, south, right, okay, negative direction. If the total mass is 250 kilograms, what is the velocity of the bike and the rider together? So we just need to isolate and solve for velocity. So we take our momentum, divide by mass. And so we have our negative in there, and we divide by mass, and you can see right away, kilograms divide by kilograms, they'll cancel. We're left with meters per second, and we get negative 28.8 meters per second as our velocity. Hopefully we remember how to convert to kilometers. All we would need to do is our little shortcut of times by 3.6, and we should get about 103 kilometers per hour. And lastly, here's a question trying to figure out the mass. And so we start with our same momentum formula, and we just need to isolate our m, or our mass. Plug in our numbers, and we can see right away our meters per second will cancel, meters per second will cancel. We're left with kilograms. So all we need to do is take 9.78 times 10 to the 3 kilograms meters per second, divided by 25 meters per second, and we have a mass of, rounded up with our significant digits, of 391 kilograms. Okay, here is a last little practice equation. Hopefully it's pretty straightforward. We're able to solve them, making sure we're able to practice in our workbooks. And this one again is just simply mass times velocity, and we can figure out the momentum. And we're just tracking that negative. It doesn't matter that it's a negative. We shouldn't be afraid of it. It's just telling us that it's moving to the left, or that L. And so make sure we practice lots, not just these video practice, but in our workbooks, making sure we're practicing lots as well. Hopefully we have made sense so far, because now we're going to start to dive into a little bits of changes of these elements, and we're going to talk about changes in momentum. Essentially, it's pretty straightforward when we're talking about just moving at a constant speed and everything else. However, in the real world, we know this does not actually happen. We have changes in speed all the time. And so the first introduction is we're going to just add in a change in speed. Pretty straightforward. And we just add in our delta symbol. Remember, that's what this little triangle says, is a delta. And what it means is there is a change. And so that change in velocity is just essentially taking your final velocity minusing your initial velocity. What is your change in velocity? Giving us a change in momentum. And so we're going to start talking about these as well when we're talking about a force, because we need something to actually slow you down. And so we have these forces. And when it's applied to a mass over a certain amount of time, the mass will undergo a change in momentum. And so the greater the force, the greater the change of momentum. And this is where we're going to tie in force is equal to mass times acceleration. And then if we expand this out, we can also have our change in momentum over time is also a force. So now we have what we call an impact force, and that's this formula right here at the top. We have this impact force right here that we're going to use. And so we talked about how we have this change in momentum right at the top, and that's what I show you right here. We have this change in momentum right here. But when we figure it over amount of time, when we have a change of momentum over a set amount of time, we have our impact force. So our impact force is here, and that's simply a change in momentum over time. Now that we've expanded our momentum formula to a change in momentum formula, here's a question that we can be asked, and what do we need to figure out? And so we see a 2,000 kilogram car traveling at 90 kilometers an hour, strikes a tree and comes to rest. Okay, here's a scenario we can imagine. If the impact took 0.23 seconds, determine the force exerted on the car. So first things first, here's our new formula, our force net or our impact force, our total force in this isolated situation. It's our change in momentum. I have my blue up here. So we can agree that we're going to be changing our momentum by going from 90 to 0. And then over the amount of time, this change in momentum over time gives us our force. So simple plug and play, 2,000 kilograms. Our velocity finals 0. We have negative 25 meters per second because remember, I do not like dealing in kilometers per hour. We want to be dealing in meters per second. Much, much simpler, making our lives simpler. Meters per second. So always convert and then divide by 0.23 seconds. What we now have is negative 217,391 newtons, or negative 2.2 times 10 to the 5 newtons. So that's a big whopping amount of force, which really makes sense when you have a 2,000 kilogram car. Chances are we're going to crumple and bend steel. And when you're going 90 kilometers an hour, coming to a stop in a fraction of a second, there's going to be a big impact. Try this question on your own. So pause it here, and I'll pick it up. So we're going to use the same formula. However, we don't have quite the dramatic change in speed, but we kind of have to make sure we're tracking our positives and negatives. And so assign directions. Okay, so let's give my negative right here to this 4.5. I'm adding a negative there, and I'm going to go with my 5 as the positive direction. Okay, and so a 500-gram rubber ball is thrown at a velocity of 5 meters per second and strikes a wall. After 0.25 seconds, the ball rebounds straight back with a velocity of negative 4.5 meters per second. Calculate the force exerted on the ball. And so we know it's going to bounce back. It bounces back slower. However, we know it's not just going to be canceling out and it's going to be like a difference of 0.5 meters per second if we didn't have them. We need to make sure we're putting in these positives and negatives to track the direction. And that's the tricky part about this one. So we can see now I've written it out and I've converted to kilograms. So always make sure kilograms is our good unit for momentum. Meters per second is our good or our best unit. Calculate the force exerted on the ball. And once we calculate it all the way through, we see our force is equal to negative 19 newtons. Now we're going to come up and introduce a new word called impulse. We've probably heard of impulse before, but what its definition is it's a change in momentum. And so this change in momentum is equal to impulse. And so what we can do now is expand on that formula we already learned about. And now we're just going to go change in momentum is equal to a force times by time. And so the way we see it right here is we had our force is equal to our change in momentum over time. Well, we can just simplify it to delta P over delta T. And so we have our much simplified version of force is equal to delta P over delta T, or our change in momentum, our impulse, is equal to force times time. How we see that is a question like this. So a raw egg falls to the floor and exerts 9 newtons over a time of 0.03 seconds. And so if you'll see on the back of your workbook, we do an egg drop demo and we talk about collisions and understanding what is the impact and impulses dealing with crashes. And so make sure to practice the lab. And so we want to figure out the impulse required to change the egg's momentum. So we're going to use our simplified formula. We don't need our speeds in this because we're going to figure out just our impulse. So we don't need our mass, we don't need our velocities, we just need this force, and we just need the time frame. And so all we need to do now is 9 times by 0.03 seconds, and we get a impulse or a change in momentum of 0.27 kilograms meters per second. So here's another practice one. Please read through it. Please do the calculations, but it's pretty straightforward. And practice, and don't forget these terms. A lot of physics is it's going to use these words that we're just not familiar with when we're problem solving and using these word equations. But think of what's actually happening, what do we need to solve for, and where's an appropriate formula, because we're not going to have all these formulas given. But in some ways, if we remember impacts and impulses, we're able to substitute and solve them. So practice is key when we're getting exposure and understanding what the heck these questions are trying to ask. So coming back to impulse, here we can see we have another egg drop. This time we do have a mass, and it's dropped to the floor, and at the moment it strikes the floor, it was traveling 4.2 meters per second. Determine the impulse on the egg. And so we were just talking about change in momentum is equal to impulse. And this change in momentum is also equal to force times time. However, I don't have forces, I don't have time, but remember, I have change in momentum is impulse. And so don't get lured in with just, okay, I'm practicing, only doing it one way. Mix up the types of questions you're trying to solve for, and don't forget about all the other formulas that we have. And so understand impulse is just change in momentum. And so we have our speeds this time we're dealing with. The last time we just had a force and a time. This time we have a mass and velocity. So our impulses, we want to use this one, using our change in momentum. So way back 4 slides or so, let's go with this one. And so right away, where did the rest go? Well, my final velocity is 0 because it was traveling at 4.2 meters per second. And I'm going to say right as it was about to hit the floor, that was my initial. And then it came to a complete stop. So its final was 0. So it was here right before impact at 4.2 meters per second. It was right here. And then at impact, it became 0, thus canceling it out. However, the key thing is it's in this negative. And so now I have my mass times by my negative 4.2 because it's going down. And so what I have for my change in impulse is 0.27 kilograms per meter per second. Exactly the same that we had before. So equaling out, we had this raw egg and this impulse equaled the impulse last time as well. So I'm going to pause it there for this video, and we're going to be left with the thought about impulses and how we have larger forces acting over shorter times or smaller forces acting over longer times. What would you prefer? And in this case, when we're crashing or having these protections, which is the best way to stop cars? Because you have to change the momentum. You want to bring the car to a stop, but what is better? Well, it depends on what the other risks are. Why would you want a solid barrier versus a collapsible barrier? What's going to actually happen? And a lot of these thought in questions. For the most part, you would want to have a smaller force over a longer period of time because it would keep the person inside the car safer. However, the issue would be is why would you want a rigid one and why would you want a large force over a short period of time? Depends what's on the other side of the barrier, or if you're trying to go through a highway where there's not enough space to actually allow a longer force to collapse everything. So both have a purpose, but just kind of think what would be the best way in the driver's situation to stop a car. So like I said, I'll pause it here. Please take time to practice lots in your workbooks. For now, take care.